Our next unit is going to be on atoms and moles, and this lesson will be on atomic structure. And in this unit, we are going to talk about four things. We're going to talk about the basic structure of the atom. We're going to talk about how to figure out the number of protons, neutrons, and electrons in any particular atom. We'll talk about how to combine atoms and in molecular formula, and how to figure out how many atoms of each type are in a formula. And we'll figure out how to determine the molecular mass of a molecule. So, first, let's talk a little bit about the atom. Atoms are basically the smallest unit of matter, the most fundamental unit of matter that still has the properties of the matter that we see, such as gold is something that you're familiar with. It's sort of shiny. It's gold-like. It conducts electricity very well, conducts heat very well. An atom of gold would be the smallest amount of gold that still has those properties, or the smallest amount of matter you divide a gold up that still has the properties of gold. Atoms, though, can be broken down into further parts. And as you can sort of see at the bottom, we have a table of the three types of fundamental particles that make up the atom. And those are the proton, the neutron, and the electron. Now, the proton and the neutron both have a location in the nucleus. And so in this case, in our drawing right here, the nucleus is at the very center of the atom, right in there. If we zoomed in, we could zoom in all the way. At this particular picture is of a helium atom. It's a helium-4 atom. And so you can sort of see they've zoomed in and they've got the picture of the helium nucleus right about there. And as you can sort of see, the unit on here, I know it may be difficult for you to see here, but it says it's 1 femtometer right there. So that gives you basically an idea of the size of that nucleus compared with, say, the larger atom, which is at 100,000 femtometers. So for the one that goes all the way from this side all the way to here. So that just gives you an idea of the size of the nucleus compared with the overall size there. So it's a little, I mean, it's somewhere in the neighborhood of in this case probably about between 1/100,000th and 1/150,000th the size of the overall atom. Now the electrons, on the other hand, are located in what's called the electron cloud, and that's the part that sort of sits out all around on the outside here. We'll talk about the electron cloud and what it means a little bit more once we get to our unit on electrons. But for right now, all it is, suffice it to say that the electrons they exist in the electron cloud. It's not a cloud in the sense that we normally think of clouds. They don't do orbits in the way that you may have seen sort of the standard third grade model of the atom. They don't sort of orbit around like planets, but they do exist in the electron cloud. For our protons are one of the two larger of the three particles. They have a mass of about 1 AMU, 1 atomic mass unit. In fact, actually, they have a mass of exactly 1 atomic mass unit for a proton. Atomic mass unit is usually just defined as the mass of a proton, so that's how we'd know they have exactly that. So for the most part, that's a very, very small unit. You would need 6.022 times 10 to the 23rd protons to make just 1 gram. So very, very small unit, but that's the mass of a proton. Neutrons are just a tiny bit smaller, but they're so very close to the mass of a proton, we consider them to be roughly 1 AMU as well. So protons and neutrons have the same mass. Electrons are much smaller, 1,836th of an AMU for the mass of an electron. So as they're moving around the electron cloud is that they are much, much smaller. And so what we'll find later is that to find the mass of any atom, you add up the protons and the neutrons. You really don't add up the electrons because the electrons are so small we can pretty much ignore them. Now, charge-wise, protons have a positive charge. That should be a positive sign there. Protons have a positive charge, while neutrons are neutral, no charge to them. Electrons are negative. And so this is something that's going to be easy. You're going to need to make sure you remember here. Some of these are fairly easy. Protons are positive. Why? Because they're pro. Pro would mean positive here. Neutrons are easy because they are neutral right there. And then you sort of just have to remember that that electrons are negative. Maybe you could say something like it's a negative experience if you get shocked with electricity, something like that. But just remember, protons are positive, neutrons are neutral, and electrons are negative. just to give you a little bit of a better idea of the size of the atom, let's suppose that if the nucleus were the size of a marble, here's a marble right here, one I'll have in class. If that were right there, the size of the nucleus, then the overall atom size for a hydrogen atom would be larger than the city of Van Meter. Substantially larger. I don't know, you really can't see this very well, but school is right there. And the interstate exit is right up here, and here's F90 going across there, and so you can sort of see there's the main part of Van Meter, just sort of right up in there. So you can see that if that marble that we saw right before were the nucleus, then the overall size of the atom is absolutely massive, just in terms of, well, just large in comparison. What this basically says is the nuclei are extremely, extremely small. So that just sort of gives you an idea of the size of the nucleus compared with the atom. Now, on to our protons, neutrons, and electrons. So you need to go ahead, and if you don't have it out already, go ahead and get out your periodic table. You will need that for the rest of this lesson. You can pause if you'd like. Now, the number of protons, to find that, very easy. It's the same as the atomic number. So if you look on your periodic table, you'll see there's an atomic number that's there, starting with hydrogen 1, helium 2, going all the way up to element 118, which has, guess what, 118. So if you want to simply find the number of protons, all you do is you look up the atomic number. So if we look at how many protons are in the following. Iron, we look up iron, its symbol is Fe, and so we see that iron has 26 as the atomic number. So how many protons does it have? 26. Beryllium, Be, that has 4 is the atomic number, so it has 4 protons. Lithium, it says lithium -4. Now we'll talk about what that -4 up there means in just a second, but for right now we say, does that affect what the atomic number is? Lithium is the atomic number of 3. The -4 doesn't affect it, so it's just 3. So protons is always the easy one to get. You just look at the atomic number and that's the number of protons, period. There's nothing that can change that, because what defines an element as an element is the number of protons. If you had iron that had 25 protons, it wouldn't be iron. It would be manganese instead. You can't have iron that has any more or less than 26 protons, because that's just the definition of what iron is. So protons is easy. Neutrons is a little more difficult. It's simply the atomic mass, whatever that is, minus the atomic number. The only thing you have to be a little bit careful with this is if you look at your periodic table, let's take a look at, say, iron again. The atomic mass of iron is 55.845. Well, if you just did this straight, the way that this one right here says, then what you'd find is you had 0.845, you'd have some fractional number of neutrons, and it's not possible to have a fractional number of neutrons. So in order to find the number of neutrons, you need to know the exact isotope number. And so that's going to be something like, say, on A right here, is he has the 56 out there. That is the isotope number. That's the atomic mass for that particular isotope. You have to know that to find the number of neutrons. Sometimes you'll have people that'll go ahead and just sort of round the atomic masses up, but that's really sort of iffy, because that would give you something that might work sometimes but isn't guaranteed. So you want to make sure that you have some indication that tells you what the isotope number is to figure out what the mass is to find the number of neutrons. So looking at our first one, iron 56, that we said that iron has a total, well, this iron 56, first thing is the atomic mass. It has an atomic mass of 56. And then we're going to subtract from that the atomic number, which you look up there was 26. So 56 minus 26. And so doing that, that tells us that the number of neutrons in iron 56 is simply 30. And so we have 30 neutrons right there. Our next one, you see we have C12 or 12C. This would normally be pronounced carbon 12. This is another way of showing what the isotope number is. The isotope number in this case is the one that is up right here. So this is carbon 12. That means it has a mass of an atomic mass of 12. And so to figure this out, we'd say the atomic mass, which is 12 here, minus the atomic number for carbon. The atomic number for carbon, if you look it up, is 6. So 12 minus 6 gives us quite simply 6. So we know we have 6 neutrons that are in this guy right here. Our next one is our lithium -4. We saw that a little bit before. In this case, the -4 that's up on the right hand side, compare that with B, where you had carbon 12. The 12 is on the left hand side. That left hand superscript tells you the atomic mass. The right hand superscript, though, is actually the atomic charge. And so this lithium -4 doesn't tell us anything about what the atomic mass is. So we really can't answer this question. We don't know exactly how many neutrons are in this one because we don't know what the atomic mass is. And so this would be an unsolvable problem right here because of the fact that we don't have that information. And so you just need to make sure that you remember to look for the atomic mass, not on the periodic table to find neutrons, but it'll be somewhere in the one that's given to you or in something else you can figure out. So that's just something to keep in mind. So onward we move to electrons. In a neutral atom, an atom that doesn't have a charge, the number of electrons is the same as the number of protons. Now this makes sense because if I had an atom that has 10 protons in it and I know it's neutral, that means I have to have the same number of negatives as I do positives. And so if I have 10 protons which are positive, I have to have 10 electrons which are negative. And so in a neutral atom, very simple. It's just the same as the number of protons, which is the same as the atomic number. We can, however, change the number of electrons that we have in an atom. We said before if we change the number of protons, it changes to a completely different atom. Electrons, though, can change and still have the same element. If we positively charge an atom, that is, we take away an electron, we subtract a minus, and so that makes a positive. Positively charged atoms are called cations, whereas if we add electrons, the negatively charged atoms are called anions. And so let's see if we can find the number of electrons in these examples. So the first one is Fe. And so it's just iron right here, just by itself. There's no indication of any type of charge. So this guy right here is neutral. And since he is neutral, then that means they're the same number of electrons as protons. And the atomic number of iron is 26. That means there are 26 protons. That means there have to be 26 electrons. And so we've got the electrons for that. The next one here, we have carbon +2. Now what that would tend to indicate, and this could be the carbon +2 or this could also be written as just C2 like this. Both mean the same thing. This means this has a charge of +2. Well, let's just sort of look at this very quickly. Let's just sort of say that, let's look at our protons. Protons, we know for carbon, according to the atomic number, is 6, so therefore there are 6 of these. If this has a charge of +2, that means there have to be 2 more positives than there are negatives. And so if there are 2 more positives than there are negatives, that means that there are 6 protons, but the number of electrons is going to have to be 4. Because there are, in this case, 2 more positives, 2 more protons than there are electrons. Note that there couldn't be 6 electrons and 8 protons. That would still be a +2 would be the charge, but it wouldn't be carbon anymore. That would instead be oxygen, because oxygen's what has 8 protons. So whenever you have a positive number for your charge, that basically means that you're going to have a smaller number of electrons than you do protons. So onward to our next one, our lithium -4, we can finally solve something for this. So the -4 tells us the charge. So if we once again look at our protons, we say for lithium, lithium has a total of 3 protons. And so in this case is that it has a negative charge. That means there are more negatives than positives. So that means that there have to be more electrons than there are protons. And how many more? In this case, -4, so there are 4 more. So 3 + 4 is 7, so there must be 7 electrons here. So that's how you find the number of electrons in various things. All right, next bit here is going to be on molecular formula. So molecular formula describe the structure of molecules. They tell you what atoms are in a particular molecule. And molecules are basically cases where you have different atoms that join together They bond together using, we'll talk about later, you basically use by sharing electrons or taking electrons, and they form a bond together, and when they do so they will form a molecule. Molecular formula, and the formula formulae, the AE is plural, so this would be, you could also say molecular formulas, they mean the same thing. Can be written sort of as is shown in the bottom of your screen here. So first case here, H2O, water, one everyone is familiar with. What this simply indicates, a subscript down here indicates that this is the number of atoms of the previous element. So that means here we know that there have to be a total of 2 hydrogens. There's no subscript after the oxygen. When there's no subscript, that basically means there's a 1. You never write that down, so you never actually would put this on here. So that you wouldn't actually write that there. But it tells you that. If there is no subscript, that means that there is 1 here. So for this particular one, we know we have 2 hydrogens, we have 1 oxygen. Now that subscript, as we said, talks to the previous element. The only exception to that is that if on the, like say on our second one here, BaOH2, if there's a parentheses, like there is right there, the 2 talks to everything that happens before it. So in this case, that 2 distributes both to the hydrogen and to the oxygen. And so writing this guy out, we have barium, we have oxygen, we have hydrogen as our 3 elements in here. Is that barium, there's no number after barium, so that means there's just 1 barium right here. Oxygen is there's no number after the oxygen here, but since there is the 2 that talks to everything in the parentheses, that means that there's the implied 1 right there. 1 times 2 gives you 2 total. Same thing for the hydrogen. There's no number after it, so the implied 1 right there times 2 gives you 2. So that means that there's 1 barium, 2 oxygens, and 2 hydrogens. If we have more than 1 molecule, that's indicated by a number out front. The out front number, as you notice, is not a subscript, it's not a superscript, it's just a normal size number. It means that there are, in this case, 3 of everything that's right here. And so 3 AlCl3s. So for this one, if we wanted to find the total number, we have aluminum, we have chlorine right here, is that we say how many aluminums do we have? Nothing after it, that means there's a 1. So we have 1 aluminum there, but since we have 3 totals, 3 times 1 gives you 3. For chlorines, we have 3 chlorines right here, but there are 3 AlCls, so 3 3s is 9. And so that's how we get that right there. So that's how you basically figure out the number of each atom in a molecular formula. So let's do some example work, get an idea of how to set this up. So this one asks how many atoms of oxygen are in each of the following. So for our first one right here, we say, alright, let's take a look. Is there a subscript directly after the O? The answer is yes, it's right there, that 2. And so in this case, there is no number out front, so that means it's a 1. We don't have to worry about that. There's no parentheses here, so that means there are just 2 oxygens in that one. This one right here, there is no subscript after the O. There's no parentheses in here, so there's just 1 oxygen in NaOH, but there are 3 NaOHs, so 3 times 1 gives me 3. 3 oxygens in number 2. Alright. Our next one, Al2SO43. So in this one, there is a 4 after the oxygen, so we have at least 4 of those, but the 3 distributes that. So that means that there are 3 4s, or 12 oxygens right here. No number out front, so we don't have to multiply it by anything. For this next one, we have 3 oxygens in that little piece right there, but the 2 distributes. So that means we have 3 times 2, we have 6 oxygens in this guy right here. But then we have another 6 out here, so we have 6 6s for a total of 36 oxygens in number 4. And that's how you'd work that out. For molecular mass. First thing, before you talk about molecular mass, you have to talk a little bit about atomic mass. And we discussed that a little bit earlier, but the atomic masses that you want to use for finding molecular mass are the ones that are on the periodic table. The only ones you won't use, the ones in the periodic table, are looking for neutrons, because those have to be whole numbers. The atomic masses that are given on the periodic table are basically averages of all the different isotopes at the levels that you'd find them on Earth. After the ding, we'll continue here. So for a molecular mass, what you have to do is the first step is to figure out how many of each atom are in your particular molecule. And so in this case right here, we have two elements. We have silicon and we have fluorine for this example. The next thing to figure out is the number, as we said. So we have how many silicons here? We have 1. How many fluorines? We have 4. All right. The next thing to figure out is going to be the atomic mass, like that. So we look at it for silicon. So silicon has, look up silicon here, has an atomic mass of 28.09. And we do want to always round these to the hundredths place. Fluorine, looking that up, fluorine has a mass of 18.998, which rounds up to 19.00. All right. So once we've got these two, the next step is basically what we can do is you multiply the number of each one times the mass of each one, and that's going to give you a total mass of each one. And so 1 times 28.09 just gives us 28.09. 4 times 19 is one that I should be able to do in my head, but I'm going to do it in the calculator just to make sure I don't make a mistake. So we said 4 times 19 is 76, and so we get 76.00 is the total amount of fluorine. And now at this point, to find the rest of this, we can just go ahead and add those two guys up. And so we would say 76 plus 28.09, so plus 28.09, and so we get a total of 104.09. And the unit is going to be AMU. For right now, we'll find there actually is another unit you can use, but this is the one that we will have for right now. So 104.09 AMU would be what we have for the molecular mass of SiF4, silicon fluoride. So on our next one, we're going to set this up the same way. This one, though, has 3 elements in it. So we have barium, we have carbon, and we have oxygen. So let's first look at our number of each one. Looking at this, we have 2 bariums. Carbons, we have 1 that's inside here, but the 3 distributes, so that means we have 3 carbons total. Oxygens, we have 3 inside the parentheses, but the 3 distributes gives us 9 oxygens. So for the atomic mass that we'll have here is the first one is barium. Looking up barium, it's sort of towards the bottom left, 137.33. Our next one is carbon. Looking that up, we have 12.01. And oxygen is our last mass here, 15.999, which rounds to 16.00 to the nearest hundredth. Once again, is that all we have to do is multiply the number of each atom times the atomic mass, and that'll give us the total mass of each one. And so once again, it's calculator time. So we take our barium, so we have 2 times the mass of barium, 137.33. And for that we get 274.66. For carbon, 3 times 12.01. We multiply that together, we get 36.03. If you do the math on that. And then our last one, 9 times 16, which gives you 144.00. That's 0.00. And now at this point, as we did before, all we have to do is just add up those 3, and that will tell us the molecular mass of this compound. So we'd say the 274.66 plus 36.03 plus 144, and doing so gives us 454.69. So 454.69 AMU, or atomic mass units. And so that right there is going to be our final answer here. on how to find molecular mass.